Hello everyone, welcome to lecture number 48 of this NPTEL course on Riemannian geometry. So we have been investigating, and we will do so for the next couple of lectures also, the problem of suppose you are given a geodesic gamma, till what time does gamma remain minimizing. So we have already seen that for some short time gamma will remain minimizing as long as it lies in the geodesic normal neighborhood. So the question is still what is the maximal time for which it remains minimizing. So in connection to that, today I will introduce this notion of conjugate points. So before that, let me remind you what we saw in an earlier lecture, I think maybe about 2 or 3 lectures back, that suppose you are given a geodesic from 0 to L to M, and let us say it is given by the exponential of t times some vector v, where we will normalize so that v belongs to the unit tangent sphere. So this is basically just the set of all tangent vectors with norm 1, right. Now suppose I have a Jacobi field along gamma which vanishes at the original at the initial point, and the derivative at the initial point is given by w, then we have this nice formula for exactly what that Jacobi field will look like. It is basically the derivative of the exponential map at the vector tv acting on the vector tw. So here, as always, so recall that the derivative of the exponential map at this point tv is basically a map from the tangent space to TPM at this vector tv to the tangent space to M at the point gamma of t, right. And the idea is that we identify, because TPM is a linear is a vector space, we identify this with TPM, okay. So the derivative of the exponential map at the vector tv is thought to be a map from TPM to T gamma of Tm, okay. So then this formula makes sense because Tw is a vector that lies here, okay. So as I said, the main point of today's lecture is to introduce this notion of conjugate points. Okay, so here is a definition. So so let P be a point in M, and let us say gamma is a geodesic such that T naught belongs to this interval and gamma at T naught is P, okay. We then say that a point Q which is gamma of T1 is conjugate to P along gamma if there exists a Jacobi field along gamma which is non-trivial. So the Jacobi field is not identically 0, which vanishes at these 2 points. Okay. And then we denote the set of conjugate points to P along gamma to be simply this set conj of P along gamma. So this is the set of points conjugate to P along gamma, okay. So let me make a remark. So maybe let me make a couple of remarks. The first point is that the conjugacy relationship is symmetric. In the following sense, that Q is conjugate to P and gamma if and only if P is conjugate to Q along gamma. Okay. The second point is that let gamma be a curve connecting P to Q, then we define the null space to basically be the set of all vectors, the set of all vector fields that vanish at the two endpoints, such that the index of I x w is 0 for all other w, right. Then we have seen earlier that from a characterization of Jacobi fields that we saw in a previous lecture, the null space is precisely the set of Jacobi fields that vanish at the two endpoints. Okay, where I am assuming that gamma is from 0 L to M, gamma 0 is P and gamma L is Q. Okay. Right, so that means that Q is conjugate to P along gamma if and only if the null space is non-trivial. Okay. So of course the trivial Jacobi field will always belong to the null space. So Q is conjugate to P along gamma as long as the space is non-trivial. And so then here is just a definition that we will not use again, but this is kind of an important definition. So the multiplicity of Q this is just defined to be the index, the dimension of this null space. So clearly because the space of Jacobi fields is 2n dimensional, once you specify an initial condition that j of 0 is 0, then the dimension of the null space is definitely going to be less than equal to n, and in fact you can take the perpendicular sorry I should say that so maybe let me also say that note that j of 0 is 0, j of L is 0 implies by something that we again did in an earlier lecture, that J has to be an orthogonal Jacobi field. So putting all this together, this implies that the multiplicity has to be can have dimension can have value at most n minus 1. So the dimension of the null space can have can be at most n minus 1. Okay, so now I want to give a characterization of the conjugate point. So here is a basic proposition. So let Q be equal to the exponential at P of V and gamma the corresponding geodesic. Okay. Then Q is conjugate to P along gamma if and only if you look at the derivative of the exponential map at V, this is singular. So when I say this is singular, that just means that the kernel is non-trivial. Okay. So conjugate points basically measure or conjugate points basically characterize the points where your derivative of the exponential map fails to be invertible. Okay. Okay, so the proof is not difficult after all that we have done so far. So let's do the forward direction. So then there exists a J in this null space, right, which is non-trivial. Now let W be equal to J prime of 0. Okay. Then because J of 0 is equal to 0, the proposition that I started off the lecture with, I reminded you that we can write down a formula for such Jacobi fields. This Jacobi field is given precisely by the derivative of the exponential map at TV acting on TW. Okay. But then if you evaluate this map at 1, so firstly because J belongs to the null space, we also have that J of 1 is equal to 0, right, because gamma of 1 is basically the point Q. But then this implies that if you just plug in 1 in this formula, the derivative of the exponential map at V acting on W is 0, and clearly W is non-zero because J is non-trivial. Okay. So this shows that the kernel of the exponential map at V is non-trivial, and the converse is basically the same. So conversely, suppose W belongs to the kernel of this map, then we look at the corresponding Jacobi field. So let this is a Jacobi field such that J of 0 is 0 and J prime of 0 is W. But now again if you plug in J of 1, this is also 0. So J belongs to the null space. Also because W is not 0, by the existence and uniqueness of Jacobi fields, this is or rather I mean J cannot be trivial, because if J were trivial then J prime of 0 would be 0, right. So W is not 0, so that that means that J is non-trivial. But then that just means that Q, which is equal to J of 1, is a conjugate point, because we have found a non-trivial Jacobi field that vanishes at the two endpoints. Okay, so that completes the proof of the proposition. Okay, so next I want to basically state a fundamental fact that and this is the reason why we are looking at conjugate points in the first place, is that geodesics stop minimizing beyond their first conjugate point. Okay, so before I do that, let me give you a couple of examples so that you get a feel for conjugate points. So let's first take the round sphere. So here we have seen that let's take our point P to be the north pole, and let's fix a geodesic. Okay. Then Jacobi fields can be constructed by simply sort of rotating the sphere, so you get a variation through great circles and then look at the variation vector field of that. So here it is clear that the only conjugate point along gamma is basically the so here P is the north pole, is basically the south pole, okay. And we indeed see that beyond the south pole your geodesic stops minimizing. Also note that the null space here is actually n minus 1 dimensional, because you take any sort of perpendicular vector to this geodesic that will correspond to a variation through geodesics, but that will keep the north and the south pole fixed, right. So that will vanish at the north and the south pole. So this happens for any orthogonal Jacobi field. So that means that the null space is actually the dimension is actually n minus 1 in this case, okay. Alright, let me give you another the other extreme example. Let us take the cylinder. So in this case one can actually show that there are in fact no conjugate points. So let us take a point P here and let us look at geodesics that pass through P. I want to claim that this actually has no conjugate point, and the reason is that this is actually you can sort of cut open a cylinder and unroll it to get a flat strip in R2, and then all the geodesics, so in general these are sort of helices, they basically correspond to straight lines, right, on this cylinder. So let us say your point P is here, then the Jacobi fields will all look like this, right. So in other words, a Jacobi field that vanishes at P will never vanish again, okay. So there are no conjugate points. In fact in this case as a nice exercise, write down the exponential map explicitly, okay. Say for P your favorite point, so we can take maybe P to be 1 0 0, okay, and check that it is actually a local diffeomorphism. Okay. So by our proposition that basically shows that there cannot be any conjugate points, okay. So this is a good exercise for you to try out. Alright, so that brings me to the main sort of result on conjugate points. So here is the proposition. So this is a sort of baby version of the index theorem. There is a vast generalization called the Morse index theorem, which is beyond the scope of this course, but this is sort of a simpler easier version of that, okay. So let gamma be a unit speed geodesic, let P be equal to gamma of 0 and let Q be equal to gamma of L. So suppose there exists an interior point such that gamma of T naught is a conjugate point, then there exists a normal vector field, admissible vector field, such that it vanishes at the two endpoints, or in other words, x is in the tangent space to the path space at gamma, and crucially the index is negative. Okay, so in particular, what this implies is that gamma is not minimizing. So as soon as you have an interior conjugate point, gamma cannot be minimizing. Okay, so what is the proof of this? So by definition, let J be a Jacobi field on the restriction of gamma from 0 to T naught, such that J is not trivial, and J of 0 is 0, J of T naught is 0. Okay, this is by the definition of gamma of T naught being a conjugate point. Okay, then consider the following piecewise smooth vector field. So y of t is basically J of t until you hit T naught, and then it is 0. Okay, so clearly y is an admissible vector field. Okay, it is continuous and it is piecewise smooth. Okay, so let so we construct an orthogonal sort of smooth vector field such that W at T naught, so one can do this using bump functions. W at T naught is simply the jump in the derivative of y prime. Okay, so that is just y prime of T naught from the right minus y prime of T naught from the left, but by the definition of y, this is simply minus of J prime of T naught from the right, left, right. Now key observation is that J prime at T naught is not 0. What is the reason? If it were, then because J of T naught itself is 0, so you have J of T naught is 0, J prime of T naught is 0, existence and uniqueness implies that J will have to be the trivial Jacobi field, right. So J prime of T naught cannot be 0, which implies that W of T naught is not equal to 0. Okay. All right. So then for delta small enough, let us consider the following vector field. X delta is this y plus a small perturbation in the direction of W. So note that W can be constructed using bump functions. So we have done this sort of construction a lot of the time, so I am not going to elaborate on this. Okay. All right. So in any case, we take this small perturbation and calculate the index. So what is the index of this? by the sort of distributive or a plus b whole squared formula, this is precisely I gamma of y comma y plus 2 delta I gamma of y comma w plus delta squared I gamma of w comma w. Okay. But now what is I gamma of y comma y? If you go back to the index formula, remember this is basically the boundary terms. So so let me write down the formula completely. So this is okay, then minus there is something that comes from the jump of the fact that y is non-smooth, but the only non-smooth point is t naught. So it will come from the jump of the in the derivative of y at t naught comma y at t naught, and then there is the main integral term which will be of the form y double prime plus r of y gamma dot y. Now y is a broken Jacobi field, right. So if because it is a broken Jacobi field, this term is 0. On the other hand, you go back to the boundary terms, y keeps the boundary fixed, so sorry, y vanishes at the boundary, so this is also 0. So by the way, I write sorry, I write a and b, I should write 0 and L. Okay, let me correct that. So this is L, this is 0, right, but y vanishes at the boundary, so all of this is 0. On the other hand, y of t naught is also 0, so this is 0. Okay, so the index of y comma y is 0. Similarly, if you compute the index of y comma w, that again, because y is a broken Jacobi field and it vanishes at the boundary and w also vanishes at the boundary, this is basically going to again involve just this jump term. Okay, but now this is minus j prime of t naught squared, which is strictly negative. Okay, so now you go back to the index formula. So the index of x delta, the first term is 0, so you can take delta common, it is going to be minus j prime of t naught plus sorry, minus 2 times this plus delta I gamma w comma w. So now does not matter what this is, there exists a delta small enough, depending of course on the value of this index of w comma w, such that this index term can be made negative. Okay, and this completes the proof of the proposition. Yeah, so for small delta this term will be tiny, so the negative term will dominate. Alright, so that proves the proposition. So now we know that geodesics cease to be minimizing beyond conjugate points. In the next couple of lectures we will explore whether this is the only way that a geodesic can stop being minimizing. Okay. Alright, so thank you for your attention, and I will see you in the next lecture. Thanks.